Hello, this is Dr. Brown. This is going to be a short video, and we're going to be covering some of the key concepts for Test 3. All of the concepts in this video have actually been covered in the chapter videos and the homework and the Test 3 review problems. I'm just going to hit the highlights and wanted to reinforce these concepts. One of the first things you'll see on the test is understanding and calculating inverse trig functions. There are examples in the homework, examples in the practice test review video problems, and in the video. Basically, if we say y equals sine of theta, then we can use inverse sine function to calculate the angle theta, because the inverse sine of theta is theta, and that's just simply inverse sine of y. So we're going to be using this quite a bit on the test, and I advise you to make sure you understand the concept of the inverse trig functions. Now, also, as you work some of these problems, I want you to reinforce your understanding of the range of sine of theta, cosine of theta, tangent theta, and cotangent theta. First of all, you need to remember that the sine and the cosine can get no bigger than 1 and no less than -1. When you graph the sine function, you remember it goes up to 1 max and goes down to -1. The same for the cosine function. So if anybody asks you, is there an angle whose sine is more than 1, just tell them it doesn't exist. However, the same is different for the tangent and the cotangent functions. You recall that we graphed the tangent and the cotangent, and both of these have vertical asymptotes that go to plus infinity and minus infinity. So the value of tangent can go anywhere between minus infinity and plus infinity, and so can the cotangent function. Now, we have already talked about some common trig identities. You recall, as we looked at the unit circle and looked at the reference triangles, remember the y value was sine of the angle, and the x value was cosine of the angle. From this, you can see that the tangent of theta is equal to the opposite over adjacent. And looking at this triangle, that happens to be sine of theta over cosine of theta. By the same token, the cotangent of theta is just adjacent over opposite, and that gives you cosine of theta over sine of theta. And you need to be able to use these identities. There will be a sheet with some of these on the test, and you'll need to use those to simplify other trig expressions. You should remember cosecant of theta is 1 over sine, secant theta is 1 over cosine, and the cotangent of theta is 1 over tangent. And then there are these Pythagorean identities, which are obvious if you look at the reference triangle. Notice that the two sides are cosine of theta and sine of theta. So you can say sine square theta plus cosine square theta equal the hypotenuse squared, which is 1. So we have what we call the Pythagorean identity, sine squared plus cosine squared equal 1. And if you divide each side of this equation by cosine square theta, notice you have sine square theta over cosine squared is equal to tan square theta, and cosine square theta over cosine squared is 1, and 1 over cosine squared is secant squared. So we have the identity tan square plus 1 equals secant square theta. Using the same techniques, you can show that cotan square theta plus 1 equals cosecant square theta. So you should be able to use these identities to simplify other trig expressions. Now, some of the simplification of trig expressions and establishing the trig identities you'll need to be able to do by factoring and sometimes canceling common terms and using common trig identities that we just talked about. So here again, you're going to have to remember how to factor expressions that could be quadratic, and all of this should have been learned back in college algebra. For instance, factoring and canceling common terms. Let's look at this expression. We want to simplify it. Notice this is really a quadratic, except it has a sign where you might see an x squared, an x, or sine square where you might see an x squared. Notice that you can factor this quadratic into 2 sine of theta plus 1 sine of theta minus 3. The denominator can be factored into sine of theta minus 3 times sine of theta plus 2. And notice that we can cancel out the common factors, and so we've greatly simplified this term to be 2 sine of theta plus 1 divided by sine of theta plus 2. So go back and brush up on your factoring, because you'll be doing this quite a bit. Also, we can establish identities or simplify identities by using some common trig identities. Here we want to establish the identity that 1 minus sine of theta over cosine of theta is identically equal to cosine of theta over 1 plus sine of theta. Very often, as we've talked about in the videos, that if you see terms with 1 minus sine of theta and 1 plus sine of theta, a very good thing to do quite often is to multiply the top and bottom, or numerator and denominator, by either 1 minus sine theta over 1 plus sine theta. Since we want to work with the left-hand side and we want to end up with 1 plus sine of theta on the other side in the denominator, let's try 1 minus sine of theta, which is what we already see, and multiply it by 1 plus sine of theta. And since we multiplied the numerator by 1 plus sine of theta, we need to multiply the denominator by 1 plus sine of theta. And let's just see what this gives us. It gives us, if we multiply the 2 top terms using FOIL, we get 1 plus sine of theta minus sine of theta minus sine square theta divided by cosine of theta over 1 plus sine of theta. Notice these cancel out and we get 1 minus sine square theta over cosine of theta times 1 plus sine of theta. And remember, with these identities, that 1 minus sine squared is equal to cosine squared of theta. And on the denominator, we still have cosine theta times 1 plus sine theta. And notice we can cancel out a cosine theta in the numerator and the denominator, and we're left with 1 cosine of theta in the numerator and no cosine theta in the denominator, and we have left 1 plus sine of theta, which is exactly what we had planned to do. So we did establish that identity. Now, one of the things you're going to see quite a lot of on this test is being able to solve trig equations. And there are various equations that you want to find the value of theta or the value of x. And it's going to be sines and cosines and tangents or tangent squares or secant squares, some combination. We need to solve these equations. We're going to learn how to do this using the unit circle. We're going to learn how to do it by factoring possibly a quadratic equation and using the unit circle. And then there are many which you can't factor, and you will have to graph the equation and solve using your graphing calculator. So let's look at those examples. One of the most simple ones you could think of is just using the unit circle and a simple equation, cosine of theta equals 1/2. Notice that we can use our unit circle here because notice cosine of theta is the x value on the unit circle. And look at the unit circle and you'll see the x value is 1/2 for pi over 3, and the x value is 1/2 for 5 pi over 3. So the solution, at least between 0 and 2 pi, for theta equal pi over 3, and theta equal 5 pi over 3. And notice we can add and subtract 2 pi multiple times. So there are an infinite number of solutions. So each of these values you could add or subtract 2 pi. But the first two solutions are the ones we list here. Another way to solve some of these trig equations is to factor the equation and then use a unit circle. So let's look at an example. 2 sine square theta minus 3 sine of theta plus 1 equals 0. And we want to solve it on the interval of between 0 and 2 pi. So let's factor this. We get 2 sine of theta minus 1, and then sine of theta minus 1 equals 0, always check that you've got the right factors by FOILing it out. And sure enough, we get 2 sine squared theta. Outside is -2, inside is -1, so it's -3 sine of theta. The last is +1, so we have factored it correctly. Now we've set each of these factors equal to 0, and we get 2 sine of theta -1 equals 0. Sine of theta equals 2 sine of theta equals 1, and sine of theta equals 1/2. And looking at the unit circle, the sine of theta is 1/2 for pi over 6, and it's 1/2 for 5 pi over 6. And so we get pi over 6, 5 pi over 6. And of course we can add and subtract 2 pi as many times as you wanted to, but since we're doing it between 0 and 2 pi, this is solution for the first factor. The second factor gives us sine of theta -1 equals 0, or sine of theta equal 1. And notice that the only point on the unit circle where the y value is equal to 1 is for theta equal pi over 2. So our solution set is pi over 6, 5 pi over 6, and pi over 2. Now, the last technique we'll use is just graphing the equation and solving using the calculator. Here we have a very simple function, and we want to solve the equation tangent of theta minus 2 tangent of theta equals -2 for theta between 0 and 2 pi. What we would do here is transform that tangent of theta equal -2 and set tangent of theta +2, adding 2 to each side. And we want to find solution to tangent of theta +2 equals 0. So we want to find the zeros of this trig equation. So with this, we have to do this on our calculator. So let me bring up the calculator, turn it on. Since we're talking about radians, it should be in the radian mode. And now we should put in the function tangent of x +2. And we want to do it between 0 and 2 pi, so x min should be 0. X max should be 2 pi. And notice that tangent can get fairly large. Let's just go ahead with -5 and +5 and graph it and see what we get. Notice we see already 2 zeros. And I'm going to show you how to find the first 0, and you can use your own calculator to find the second one. What we'll do is hit second calc, and before we do that, we should put the trace on, and I would move the cursor to the left of the first 0. Now hit second calc and hit 2 for the 0. It'll ask you for the left bound, hit enter. Then it asks you for the right bound, hit enter. When it asks you for the guess, don't guess, just hit enter. And notice it tells you that the X value is 2.034439, which is what we have here. If you go over and you find the other one, you'll find that it is 5.1760266. So it's very easy to use the calculator to solve a trig equation. The last thing we want to do is be able to find the inverse function of a trig function. There are examples in the practice test. To sort of review how you calculate an inverse function, you write y equal f of x. Then you interchange x and y. Everywhere you see a y, you put an x. Everywhere you see an x, you put a y. So you write x equal f of y, and then solve for y. And then the inverse function of x is equal to that y that you just solved for. Simple example will explain this. Suppose you want to find the inverse function of f of x equal to sine of x minus 1. So we write down y equal to sine of x minus 1, and we interchange x and y, and we get x equal to sine of y minus 1. And now we want to solve, let me erase that, x equal to sine of y minus 1. And now we want to solve for y. So first, we want to get 2 sine of y by itself. And that would equal x plus 1. Obviously, what we did was add 1 to each side. Now we want to solve for sine of y. Would be x plus 1 divided by 2. And to solve for y, we take inverse sine of both sides equals inverse sine of x plus 1 over 2. Inverse sine of y, the inverse of a function is always going to be the y coming back. The inverse sine of y is always going to be y. Unless, by the way, you were saying the sine of y was larger than 1, so watch out for that. But anyway, solution to this is y is equal to inverse sine of x plus 1 over 2. And that is the inverse function of x. So that is the really short review video. Good luck to everyone.